All right, so we're going to start with the integral test. And before we jump into that, we are going to talk about the harmonic series. Harmonic series. Very important series. A lot of class time developed these. N equal 1 to infinity. Sum 1 over n. So what does this look like? With n equal to 1, that's 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, forever. The question is, does this series converge? Well, the test we have in our toolkit right now is the nth term divergence test. And this is a test for divergence, not convergence, okay? And so when I run the nth term divergence test, I look at the nth term and I take the limit of that sequence, an, and I get the limit as n goes to infinity of 1 over n, and this gets me 0. So what does the nth term divergence test tell me? The divergence test tells me if I get something equal to 0, then the test fails. All right. The only time this test is good is if I get something that's like non-zero, like maybe 10, and then that means if it limits to 10, then at some point we're adding 10 an infinite amount of times, and therefore the series itself will diverge. But here it limited to 0, so we don't know. The test ends up failing for that scenario. So let's do mini proof. Okay, I put proof in quotations because it's not exactly formal, but it gets the job done. N equal 1 to infinity of 1 over n is equal to 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus 1 sixth plus 1 seventh plus 1 eighth plus 1 ninth plus 1 tenth plus dot 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 plus 1 over 16 plus 1 over 17 plus dot dot dot. All right, you get the picture, right? Kind of annoying how we did this. Now, there was a reason for all this madness here, okay? This sum is greater than or equal to, well, I'm going to put 1 here to match that one there. I'm going to put 1 half here to match that there. But now I'm going to do something interesting. I'm going to take this and this here, and I'm going to say that that is, here, let me fix these colors. I'll do red there because it matches that red. I'm going to say that this is 1/4 plus 1/4. Okay? So why did I do this? Well, this will be apparent for us in just a little bit. Okay? And then I'm going to take these 4 terms here, and I'm going to make them all 1/8. 1/8 plus 1/8 plus 1/8 plus 1/8. Okay? And then I'm going to take these terms here, 1/9 through 1/16, and I'm going to add that up, 1/16 plus 1/16 plus dot 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 plus 1/16, and so on. And I'm going to continue this pattern ad infinitum. Now, why is this true? Why is that true? If you think about it, like if I just look at this part right here and this part right here, look, 1/4 and 1/4 are the same, they're equal, but 1/3 is actually bigger than 25%, 1/4. So that's why this is less than or equal to here. okay? So that 1/3 plus 1/4 is greater than or equal to 1/4 plus 1/4. Now, why did I make it 1/4 plus 1/4? Well, this is equal to 2/4, which is equal to 1/2, okay? So this is equal to 1 plus 1/2 plus, and this is equal to 1/2 plus, this is equal to 4/8, which is another 1/2 plus, and this is equal to 8/16, which is another 1/2 plus, and then you just continue the game, and what's happening? You're adding 1/2, 1/2, 1/2, 1/2, 1/2 infinitely many times. You see how I can group them together to make it to where I add 1/2, 1/2, 1/2 infinitely many times? So that is the idea of what's going on there. All right, now what happens if I add a half infinitely many times? I get half of an infinity, which last time I checked, half of infinity is still infinity. So this sum diverges, and it's smaller than the series n equal 1 to infinity of 1 over n. Okay? So this thing, which we found is actually smaller, that's smaller than the one above it. And if the small one diverges, by golly, we know for sure that the bigger one is going to diverge. Okay? So, therefore, the harmonic series diverges. Okay? Now, recall the integral from 1 to infinity of 1 over x dx. This is equal to the limit as b goes to infinity of the integral from 1 to b of x to the negative 1 dx, which is equal to what? It is the limit as b goes to infinity of the natural log of x from 1 to b, which equals the limit as b goes to infinity of ln b minus ln 1, which equals to infinity minus 0, which is divergent. Okay, so what is this telling me? The area under the curve for that function, 1 over x, this area is diverging, okay? So what does that tell me for the series here? Well, that is the integral test, okay? You notice how both this series diverges and then this integral also diverges? That, in essence, is the idea behind the integral test and why we did this problem to hopefully plant the seed for the integral test. So the integral test. All right. So there's a couple of conditions we have to meet for the integral test to hold. So for number 1, the function fn is defined as equal to an for n greater than or equal to 1. Now, sometimes the first couple of them don't work, and that's okay. If you have a scenario where like n equal to 1 doesn't work or n equal to 2 doesn't work, you can, and it's just a finite number of them, then we can just treat those like that and individually, and then look at from some point on, maybe like n greater than or equal to 5, it works from then on. And so you would consider n equal 1, 2, 3, 4 as individual cases, and then, you know, write it up from n greater than or equal to 5. Okay, so except maybe a finite number of terms. Okay, so very important concept there. Make sure you understand. If you don't get that, email me and we'll get it figured out. Okay, so that's number one. Number two that has to be satisfied. Okay, f is continuous. Okay, continuous for x greater than or equal to 1. Number three, f is positive for x greater than or equal to 1. And number four, f is decreasing for x greater than or equal to 1. And the same rule applies here. Okay, so except maybe a finite number of terms going on. So if those four things are true, okay, if that is true, which is kind of hard to show all four of them are true, that's why we kind of use integral test as a last resort, then the series n equal 1 to infinity of an and the integral of 1 to infinity f of x dx either both converge or both diverge. Okay? So what is the integral test saying here? The integral test says if we can satisfy these four bullets, so say, for that one we just did in our example, that series n equal 1 to infinity 1 over n, okay? So I need to come up with a function f of n where it's equal to the an's. Well, this is pretty easy. F of n is 1 over n, okay? And this is for n greater than or equal to 1. All right, that's true for all those n's. All right, and I know that 1 over n is continuous. 1 over n looks like this. The only place it's not continuous is at n equal to 0, because you think about it, you can't divide by 0, right? It's continuous. It's positive. It's greater than 0. And it's decreasing, looks like it's decreasing for x greater than or equal to 1 for all of those. So when we find that this integral diverges, what does that tell us? That tells us that the series has to diverge, okay? So that's how we use the integral test to prove this, all right? So let's work through an example where we use the integral test. So here's an example. Series n equal 2 to infinity 1 over n ln n. Okay. This thing right here, 1 over n ln n. Well, we just determined that 1 over n diverges, right? Is 1 over n ln n bigger or smaller? It's actually smaller than 1 over n. Okay? So maybe there's a chance to converge. All right? So maybe there's a chance, maybe not. But if you knew that the big one diverged and then this one was even bigger than the one that diverged, then what would you know? You would know that this one would have to diverge. But that's not the case here. It's actually smaller, so we're not for sure. Okay? So let's see if we can figure it out with the integral test. I need to come up with a function fn. So I'm going to use fn equal to 1 over n ln n for n greater than or equal to 2. Why does 2 a good one to start at? Well, if n equaled 1, the natural log of 1 will be 0, and I divide by 0, and that's a no-go, right? So good thing it starts at 2. Okay, so my function f of x, 1 over x ln x, okay? Is it continuous? Is it continuous? Well, the only place it's not continuous is when the denominator is equal to 0, and this is equal to 0 for x equal to 0 and ln x equal to 0, so e both sides, I get x equal to 1, okay? So x equals 0, x equal to 1, discontinuous. So that means that f is continuous for x between 2 and infinity, okay? Or you can write x is in 2 to infinity. Either one. Continuous, x to infinity. So that's the first thing. Okay, so this is what I'm looking for on your exam. I'm looking for you to tell me each part. So that's number 1. Number 2. What do we have to do for number 2? Number 2, okay, so, sorry. Number 1 was write the function, okay? So number 2 was continuous. Number 3 is positive. Okay, so f of x has got to be positive, okay? Positive greater than or equal to 0 for x greater than or equal to 2, right? So is that true? 1 over x ln x. Is this positive? Well, if x is greater than or equal to 2, then the natural log of x is greater than or equal to a natural log of 2, and that's like 0.69 or 69 maybe? I don't know, let's see, I'm not really sure what the natural log of 2 is. Just old time memory, right? So let's see, ln, where's that button? ln 2, 0.693. Okay, so yeah, so we're still dealing with something positive there. So if both of those are positive, then x ln x multiplied together is still positive, right? And so if that's true, then 1 over x ln x is still positive. So we're good. So we're positive. All right, this is a positive number. So that's the second part right there. Okay. A lot of work to use the integral test. All right, number 4. Number 4 is going to be decreasing. Okay. Now, to prove decreasing, instead of just saying, look at the graph, right? We have to take a derivative. Okay? F prime of x needs to be less than 0. Okay? If f prime is less than 0, that tells me that f is decreasing. Okay? So I just proved that over here f is positive for x greater than or equal to 2. So I forgot to write that down. So make sure not to be like me and forget to write that. Okay? So I want to show that f is decreasing for x greater than or equal to 2, right? So how do I do that? I take the derivative. So the derivative, oh my goodness, this is fun. Okay. The derivative 1 over x ln x is a quotient rule. So derivative of this, low d high minus high d low. Okay, so it's x ln x. Derivative ln x is 1 over x plus ln x. Derivative of 1 of x is 1 over x ln x all squared. So f prime is equal to this, and this is equal to minus, and then x over, and that's a 1 plus ln x over x ln x squared. The bottom piece here is positive. The top piece here, if x is greater than or equal to 2, then this 1 plus ln x is greater than or equal to 0. So that's positive, but then I have a negative here. That's a negative number divided by a positive number. That means that's less than 0. So now we've just shown that f is decreasing. Okay? So we've done everything we needed. We needed to set up a function. We needed to set up that it was continuous, positive, and decreasing on x greater than or equal to 2, since our series started at 2 here. We've done that. Now all we have to do is integral. An infinite integral. So the integral from 2 to infinity of 1 over x ln x dx. Okay? This is equal to, well, how do we do this problem? First thing I would do is figure out the indefinite integral, and that's going to help us out. Because here we've got to turn this into a proper integral, 2 to b, 1 over x ln x dx. Okay, so let's just try to figure this out on its own. How could we do this? 1 over x ln x. Okay, well, when I look at this problem, I see ln x here. That's giving me a fit. But the derivative of ln x is right here. Okay? So if I see the derivative in the function itself, I should think u sub. If I think u equals ln x, then du is 1 over x dx. And so this becomes the integral 1 over u, and then this orange part right here, that can be replaced with du. So this is the natural log absolute value of u plus c. But u is ln x, so really my integral is ln x, right? What fun is that? Okay, so now that I've done my scratch work, it makes my problem a little bit better. Okay, so now this is going to become limit as b goes to infinity of, and I'm going to write my integral in here, the natural log of x from 2 to b. So what does this equal? It's the limit as b goes to infinity of ln b minus ln 2. Okay? And when I run through this, limit as b goes to infinity, this is equal to infinity. As I plug in ln infinity, I get infinity. So this is infinity minus ln 2. All right, so that's just a number. So infinity minus a number is equal to infinity. So this diverges. So what do I write here? All that work, and I got that the integral diverge. Therefore, by the integral test, the series n equal 2 to infinity of 1 over ln, or 1 over n ln diverges since the integral from 2 to infinity 1 over x ln x dx diverges. Okay? And that's it. All right, and that gets you full credit right there. Hopefully that helps you see how to do that type of problem. Now let's do one more kind of like this and just make some notes, okay? So I want you to see where it works. So series n equal 2 to infinity, okay? And I'm going to do 1 over n and then ln n, but instead of just ln n, I'm going to square ln n. So maybe this will help, maybe it won't. But we saw here, we talked about this, that the 1 over n definitely, so like 1 over x wasn't strong enough, it wasn't going down to 0 quick enough. And then we thought, well, maybe if we added in an ln x, that would make it go down quick enough. And it turned out that wasn't quick enough to make our series converge. So now the question is, it's kind of like we're getting, a little snarky, and we're saying, well, if that didn't work, what if we tried 1 over x ln x times ln x, right? Ln x squared. And so then the question is, will this be fast enough at this point? Maybe it will, maybe it won't. So let's just look and see, okay? So let's take f of x equal to be 1 over x ln x all squared, okay? Now, is this continuous? Yes, just like for our same reasoning, continuous. So f is continuous for x greater than or equal to 2. It's only discontinuous for x equal to 0 and x equal to 1 still, okay? That work is above. All right, f is positive for x greater than or equal to 2. Absolutely it is. If x is greater than or equal to 2, 1 over x ln x squared is also going to be greater than or equal to 2, since 1 over x is positive, right? We know this to be true, then 1 over x has got to be positive. And then 1 over ln x squared, if I square something, it's going to for sure be positive. So that makes that true. Positive number and a positive number. Okay, and we know that it's greater than or equal to 0. It's greater than 0 for sure, because x is greater than or equal to 2. And then f continuous, we could use decreasing for x greater than or equal to 2. The good thing about decreasing is if you take the derivative and the derivative is continuous, then you know that the original function is continuous. So you kind of get that for free, okay? So taking the derivative is helpful because it can knock out the continuity and the decreasing at the same time, okay? So is it decreasing? Well, since x and ln x squared increase on x greater than or equal to 2, then 1 over x and 1 over ln x squared decrease on x greater than or equal to 2. Okay? So if one function is increasing on an interval, then the reciprocal of that function is going to decrease on that interval. So that's a little trick you can use too. I'm just trying to give you different tricks on how to show things are decreasing or increasing. So you can take derivatives or you can use little tricks like this. Okay? So now that we have all 4 of these, we can run the integral test. So now we can use the integral test. It's very important that these techniques, in order to use the integral test, we have to satisfy those 4 conditions first, okay? If you can't satisfy those 4 conditions, then you can't run the test. You know, one thing I talk about, it's kind of like, man, I see a really cool looking Ferrari in the parking lot, right? The only way you're going to get in and drive that Ferrari also is if you've got the keys. And the keys are the conditions, all right? So unless you've got the keys to your vehicle, you can't start the car, right? Unless it's like a push to start or whatever. But you get what I'm trying to say here. We need the keys in order to run this vehicle. And my vehicle here is the integral test. 2 to infinity, 1 over x ln x squared dx. Now, let's do, once again, a u sub, okay? U equals ln x du equals 1 over x dx. And so what does that get me in my side integral? That's 1 over u squared, right? Du. I plug a u in here, it's u squared. And so this integral is negative 1 over u, okay, plus c. So what does that equal to? That's negative 1 over ln x. Ooh, this looks promising. It looks a little different, right? So what does this become? It's the limit as b goes to infinity of, okay, and then our integral, when we integrate, is 1 over ln x from 2 to b. Okay, so from 2 to b. So what is this going to be? This is going to be the limit as b goes to infinity of minus ln of b minus ln of 2. Okay, what does this equal? This equals, well, limit is b goes to infinity, ln b, that's ln infinity, that's negative 1 over infinity. And then minus a minus becomes a plus 1 over ln 2. So this goes to 0, and this becomes 1 over ln 2. Wow, that is interesting, 1 over ln 2. So what does this say? Therefore, by the integral test, always tell me what test you're using. Since the integral 2 to infinity 1 over x ln x squared dx converges, then so does the series n equal 2 to infinity 1 over n ln n squared. Okay? Pretty cool, huh? Now, a side note, okay? And an important concept. Okay? Because this sometimes causes confusion for students. The integral from 2 to infinity of 1 over x ln x squared dx is equal to 1 over the natural log of 2. That's a number. But this does not equal the series from n equal 2 to infinity of 1 over ln or n ln n squared. It doesn't equal, okay? The series here, this is different than the area under the curve. Okay, it's different. It's not the same. So just to give you an idea, okay, what we're finding here okay, from 2 to out to infinity, that's area under the curve. That's all the area under that curve there. That's equal to 1 over ln 2, okay? That's different than the series, which takes that same curve, okay? But instead of the curve, you only evaluate it at the positive integers. Remember, a sequence is only defined at the integer values, right? So instead of having the curve, what do I have? I've got these dots here. Okay, and so I'm adding those values together. 1 over 2 ln 2 squared. 1 over 3 ln 3 squared. 1 over 4 ln 4 squared, and so on. Okay, the curve is no longer in there. You guys see how that is completely different than adding this area? So would it make sense for these to be equal? Not at all when you see the picture like this. Okay, so hopefully that will help you out. Okay, it's almost like we're finding areas of these rectangles here. Okay, so maybe we're doing like left endpoint rectangles. Okay, and you learned in calculus that the rectangle sum is a good estimate, but it's not exactly equal to the area under the curve. Okay, so that's what's going on there. All right, guys. Well, hopefully this video was helpful, and then I'm going to talk about P-series and go from there.